Yeah, it's so great to be here at Python WebConf today. Thank you so much for joining my talk. I know there's a lot of really great options to pick from this morning or this afternoon, wherever you happen to be. So as Ched said, I'm Jodie Birchall, and I'm currently working as a developer advocate in data science at JetBrains. And in today's talk, what I'm going to be doing is showing you some ways in which vectorized operations in Python can help speed up your code, as well as explaining a bit of the linear algebra behind these operations. So why did I decide to do this talk? Well, if you're anything like me, when you first started learning to program, and I first started learning to program in Python, I'm a self-taught Pythonista, for loops were your bread and butter. However, a lesson that I very quickly learned, and unfortunately I learned the hard way, is when you hit any sort of scale, loops start to get really slow. So when this first happened to me, I was Googling around, I was trying to work out what to do, but I couldn't really understand what I was reading about. So a few years ago, I did a course about linear algebra, and this finally helped me understand all this stuff that I'd been seeing about vectorized operations in NumPy. And I realized this was the key to getting those performance gains that I'd been looking for. So what I'd like to do in this talk is to give an overview of a few ways in which you can use vectorized operations to speed up your Python code. And we're going to be doing this by iteratively improving a machine learning algorithm called k-nearest neighbors. So why did I pick this algorithm? Partially, I picked it because I'm a data scientist, but I also think that this is a really great way to show off how a naive implementation using loops and lists can be really slow. And it's also a great way to showcase how you can improve your code performance using these vectorized operations. So don't stress if you're not a data scientist, you're not a machine learning engineer, if you have no interest in these topics, you can still get some value from this talk. So where will we start? What will we cover? We're going to start by going over some basics of linear algebra, and then we're going to go through how k-nearest neighbors works. We're then going to start with an unoptimized implementation of k-nearest neighbors, which relies on loops and lists. And we're going to use this as our baseline. We're going to see how long it takes to run. Then for the remainder of the talk, we're going to go through 3 different stages of optimization of our code. And at each stage, we're going to replace an inefficient part of the code with something vectorized and faster. And at each stage, I'm going to explain why these vectorized operations work by explaining the mathematical principles behind them. And then finally, we're going to end by doing a quick overview of why it's faster to use these vectorized operations rather than using loops and lists. So let's start from the beginning. Let's jump into some linear algebra. So the most basic unit in linear algebra is a vector. So you can see 3 examples of vectors here. They're basically ordered sequences of values. So in the context of machine learning, vectors are used to represent data. And you can see that here. Here I have an excerpt of a data set that we're going to be using throughout this presentation. This data set describes the physical characteristics of pictures of beans. It's a little bit of a weird data set, but it has some really great properties for what I'm trying to show in this talk, so I've just gone with it. So what you can see are 2 of the columns, the major axis length and the minor axis length, basically how long and wide the picture of the bean is. And what you can see is each of these rows corresponds to the vectors we have here on the left. So each of the vectors is essentially representing one of the beans, with the first element in the vector representing that major axis length and the second representing the minor axis length. So pretty straightforward. So what do these vectors represent in terms of linear algebra? And they represent a lot of things, but for the purposes of this talk, we can think of vectors as coordinates in an n-dimensional vector space. So what's a vector space? I find the easiest way to think about it, as with many things in linear algebra, in 2 dimensions. So let's have a look at a scatter plot of some beans against their values for the major and minor axis lengths. So what this plot is illustrating is a 2-dimensional vector space, and that major axis length represents the first dimension, and the minor axis length represents the second dimension. And each of the points represents a vector in this vector space. And you can see that with the vectors we were looking at in the last slide. It's pretty straightforward. So the beans data set we're going to be working with has 16 feature columns in total, And I can represent each bean as a 16-element vector, and that lives in a 16-dimensional vector space. So we obviously can't visualize that, but what I want to emphasize is that the principles that we can apply to two-dimensional vector spaces translate directly to vector spaces with any number of dimensions. It's one of the beautiful things about linear algebra. So now we've covered vectors. Matrices are actually pretty easy to understand. They're just simply a collection of vectors from the same vector space. So you can see here we have 3 of our two-dimensional vectors, and because they all belong to the same vector space, we saw that on the previous slide, we can put them together in one matrix. So if we bring that back to the dataset concept, this matrix is conceptually equivalent to our data frame containing 3 bean data points with 2 columns. So 1, 2, 3, and then the columns. So how does NumPy represent these concepts? It represents matrices and vectors in a data type called an array. Arrays, unfortunately, have their own concept of dimension, and it differs from how we've been discussing it in the context of linear algebra. So the way I think of dimensions in arrays is the number of sides in which an array can change size. So let's have a look at that first with one-dimensional arrays. This is how vectors are represented. And vectors only ever change size in terms of the number of elements they contain. So you can see that here. Vectors will always have a size of 1 in this direction, but they can range from 1 to conceptually infinity if you have enough space to store it in this direction. And arrays also have a property called shape, and this tells you the size of each dimension. So for this 1D array, we only have 1 value in this shape tuple here, 2 to represent the number of elements in that 1D array, in that vector. Matrices are unsurprisingly represented in two-dimensional arrays, and that's because we can have information about both the number of elements and the number of vectors in the matrix. And you can see that here. Here we have the number of elements. Here we have the number of vectors. And then unsurprisingly, the shape tuple has 2 values, number of vectors, number of elements. And then finally, a more complex concept in NumPy is that of n-dimensional arrays. So this is essentially where we reshape 1 or 2 dimensional arrays so that they sit in a higher dimensional space. So you can see that here. What I've done is I've reshaped this 2-dimensional array so it now sits in a 3-dimensional space. And we have 3 dimensions. The first dimension actually now represents the number of matrices that we have. The second represents the number of vectors, and the third still represents the number of elements in each vector. So we're going to be using this concept of 3-dimensional arrays quite heavily later on, so just hold on to this concept. And then I just want to briefly go over how k-nearest neighbors works at a very high level. So a useful property of vector spaces, it seems quite obvious when you think about it, is that vectors that are close to each other tend to be similar, and vectors that are distant from each other tend to be dissimilar. So we can see that here in the 2-dimensional vector space, where beans of the same type, represented by the same color, tend to be close to each other, and those that are of different types tend to be far away from each other. So there are a lot of different ways, many, many different ways of measuring distance within vector spaces, but the one that I want to look at today is one of the most fundamental, the Manhattan distance. So the way that I think of the Manhattan distance, the way I think of calculating it is, imagine that you're in a 2-dimensional vector space, and the only way you can travel between 2 points is by traveling along the x and the y axes. You're sort of locked into these directions. So if we say we want to travel between this point B here at 2, 1 to point A at 4, 3, we could go 2 points or 2 units along the x-axis, and then another 2 units up along the y-axis. So if we count the total number of units that we've traveled, we have 4. But you don't really want to work out how to calculate distance manually like this. So you can, of course, do it computationally. And the way you do this is you subtract the x values from each other and the y values, take their absolute value, and add them together. So, of course, we can make a formula for this, and that's the Manhattan distance formula. And what this is telling us is that we want to take the sum, like we did here, of all of these absolute differences for each element of each vector. So if I subtract the first element, the second element, up to the nth element, then what I can do is sum them together, and that will give me the total Manhattan distance. And then finally, let's go over how k-nearest neighbors works. So what we're going to do is start with a data set, like many things in machine learning, like everything in machine learning, and we split it into a train and a test set. And then what we do is we take one point from the test set at a time. Let's say it's represented by this orange dot, and we calculate its pairwise distance to every single one of the points in the training set. So we could use the Manhattan distance for that, and we will be using that in this demonstration. And you can probably guess this gets computationally quite expensive, especially if you have a big training set. Then what we do is we sort every single one of these training points by its distance to the test point, and we keep the k-nearest ones, hence the name of the algorithm. Then what we do is we basically get the labels of these nearest training points, and then we check which of them is the most frequent. In this case, it's Cali. So what we then do is we assign the label Cali to our test point. And that's how we get the label of every single one of the points in our test data set that are unknown. And again, you can probably guess that you then need to repeat this for every single one of the test points. So again, this can get very computationally expensive. So now we've covered all of the theory, we can move on to the code. We're going to have a look at creating our first implementation of KNN, or the k-nearest neighbors algorithm, in Python. And we're going to time how long it takes to run it with a few different samples of data in order to get our baseline. So let's have a jump over to PyCharm and check out our code. Okay, so what we have here to start is a function to calculate the Manhattan distance between two vectors at a time. So just two vectors. So what we have here is each of the vectors input into the algorithm as a list. And what we then do is we use this for loop here to go over every single one of the elements one at a time, take the distance between them, and then apply the absolute difference to that distance calculation. And then we just sum them together at the end, like we did with the Manhattan distance formula. We then need to get each of the pairwise distances between all of the training points and all of the test points. So we do that in this function here. What we do is we import all of the training observations and all of the test observations as lists of lists. We then use this gnarly for loop here, nested for loop, in order to go through each of the training observations and each of the test observations and permute between those combinations and calculate each of the Manhattan distances. And then what we end up with is a list of lists containing all of those pairwise differences. What we then need to do is, for every single one of the test points, is calculate those most likely labels. So that's what this function does here. For a single test point, what this does is takes in the distance to every training point and the labels of those training points. We then zip them together as a list of lists, and we sort them based on how close they are to the test point. And then finally, we iterate through that list of lists in order to extract the labels of the most closely related training points. And then finally, we need to repeat that for every single one of the test points. And that's what's being done in this function here. Okay, great. Now let's have a look at the data we're going to use to test this out. So as I said, we're going to be using this data set of pictures of dried beans, and it has around 27,000 observations. And what it has is 16 feature columns. The 17th column just contains the labels of what the type of bean is. And what I've done is I've actually created 3 different data sets from this full beans data set: a small, a medium, and a large. I'll explain why in a second. But just to describe the 3 data sets, what we have in the small data set is 3 feature columns and around 4,000 observations. In the medium data set, we have those same 3 feature columns, but this time we have actually all of the observations, so 27,000 observations. And then finally, we have a large data set, and that's really just the whole data set. So 16 feature columns and all 27,000 of the observations. So the reason I did this is there are 2 things that can influence how efficient the algorithm is. The first is the number of features, so basically the length of the vectors, and the other is the number of observations. So I want to see, or I want to demonstrate how changing different things into vectorized operations can actually affect be affected by either the number of observations or the length of the vectors. So now we get to the exciting part. Let's see how slow our unoptimized algorithm was. So for the small data set, which was tiny, we're already taking around 15 seconds to run everything. This is really inefficient. When we go to the medium data set, we're already up to 12 minutes. And for the large data set, we jump up to an eye-watering 38 minutes. So what happened here? Why is it so inefficient to go between the medium and the large data set? Why are we seeing such a large jump in the timings? Well, let's have a look at where we can get our first code improvement. The main culprit comes from how we're calculating the distance between two vectors in the first function. So as I mentioned, this is calculated using a for loop. And we're doing those differences one by one. So it means that because in the large sample we have 16 features and in the medium sample we only have 3, we're seeing a consequent scaling up in the computation time because we only have to calculate 3 differences at a time for the medium data set and the small, but we have to do 16 at a time for the large data set. So the first way we're going to shave off some time is by getting rid of this for loop, unsurprisingly. And in order to understand how we're going to do this, we first need to cover a little bit more linear algebra. So it's possible to do a number of arithmetic operations on vectors and matrices. These include addition, subtraction, and multiplication. And obviously, for our particular use case, being able to do subtraction is really interesting. So subtraction is really easy. All you need to do is have 2 vectors or matrices of the same size, as you can see here. And what happens is each of the elements line up and you end up with a vector or matrix of the same size containing those element-wise distances. So super duper easy. And then something else you can do with vectors is apply operations to each element. So these all involve passing vectors or matrices through a function. And then you basically get a vector or matrix of the same size with that function applied to each element. So you can see that here with the absolute value function, which is obviously very interesting for us. You can see this matrix M, and what we've done is we've passed that through an absolute value function that's applied to every single one of the elements. And what we get is a matrix of the same size, which has the absolute value of each element. So let's see how we can use this to improve our function to calculate the Manhattan distance between the 2 pairs of vectors. So let's jump back over to PyCharm and see how this works. So what you can see is quite a big difference to this first function. Instead of passing in our 2 vectors as lists, we're now passing them in as NumPy arrays. And if we go down to where we used to have that for loop, instead, what you can see is that we now use this very elegant subtraction notation. There is also a subtract method in NumPy, but you can also do it this way, and I think it's a little bit more readable. Then what you do is you pass that differences vector, or that vector containing the pairwise differences, through the absolute value function from NumPy, and then you end up with a nice normalized vector containing all of the differences. And then you just sum that like we did in the last function, and voila, that's it. You're done. So let's see how much this improved our timings. If we go down to the small data set, we're now down to about 8 seconds. For the medium data set, we're down to around 7 minutes. And the best is for the large data set. We're now down to around 9 minutes, which is not bad. So if we have a look at this as a function or compared to the baseline timings, essentially what we end up with is around 1.8 times faster after this improvement for the small and the medium. But for the large data set, we are almost 4 times faster. So this is great. We've managed to make some good performance gains. But the problem is we haven't made much of a dent in the computation for the small and the medium samples. And one of the main culprits for this is a nested for loop, the one that we're using in that second function, to calculate all those pairwise distances between each test observation and every train observation. So as you may know, once you start nesting loops, you end up with a bunch of sequential operations that you need to calculate. And the number that you need to calculate is a product of the number of elements in each list, because you're basically doing a permutation between every combination. So for our examples, even with our teeny tiny small data set, we're already running 3 million sequential operations in order to get those distances between each list. And then when we hit the medium and the large samples, we're already pushed up to 140 million sequential distance calculations. And we're dealing with a relatively small data set here. If we're talking about typical machine learning data sets, we can easily have hundreds of thousands or even millions of observations. So the using nested for loops can be prohibitively expensive. Like sometimes it's just not going to be feasible. So obviously we're going to try and get rid of this nested for loop and replace it with something vectorized, but we need to just do a little bit more theory in order to expand what we've already covered about vector subtraction. So to start, let's imagine we have these three vectors, x, y, and z. And what we want to do is calculate the pairwise distances between them. So this is what we've been doing with the nested for loop so far. So let's start with trying to simplify getting the difference between each vector and the x vector. So one way we can do this more efficiently than by using a for loop is by combining all three of the vectors, x, y, and z, into a single matrix. And we can do that because they come from the same vector space. And then what we do is we create a second vector, which contains a second matrix, which contains 3 copies of that x vector. And because these are the same size, we can do vector subtraction. And so we end up with a nice matrix containing all of those pairwise differences. So this is a great improvement, but you might have spotted one problem. We're going to have to use a for loop, right, in order to complete this exercise for the y and the z vectors. Well, this would be the case if we were restricted to using 2D arrays like we have been so far. But as we know, fortunately, NumPy supports 3-dimensional arrays, and that means we can actually do everything in one pass. So let's see how we might do this. We'll take our first matrix first, and this is represented here in NumPy as a 2-dimensional array. So 1 copy of x, 1 copy of y, and 1 copy of z. What we can do is we can actually recast it or kind of put it in a 3-dimensional space. And what we now have is a 3-dimensional array of size 1, 3, 4. So what we can then do is replicate this 3 times, so another 2 copies, and squash them all into the same 3D array. And we end up with a 3 by 3 by 4 3D array. We can then do something similar with the matrix, which contains 3 copies of the x vector. So we first reshape it into a 1 by 3 by 4 3D array. We then create a similar array containing 3 copies of the y vector and another containing 3 copies of the z vector. Squash them all together into the same 3D array. We end up with another 3 by 3 by 4 3D array. We can then just do a straightforward vector subtraction because, again, we end up with an array where every element lines up and we can do it all in one pass. So this is a massive improvement in terms of the computational efficiency of the operation because we're no longer bound to this sequential processing of each difference. But you might have noticed another inefficiency. We are now creating a memory inefficiency because we have to replicate explicitly each vector 3 times in our 3D array. So how do we solve this? Luckily, NumPy has another trick to help us here, and this is called broadcasting. This is essentially a memory efficient way for NumPy to do the sort of operation that we just did without the need for explicitly replicating the vectors within the array. So the way that it works is if we want to do an operation with 2 arrays, NumPy will first compare them and check if they have the same number of dimensions. In our case, this is not always how broadcasting works, but just for our example. If so, it's then going to check whether the arrays have the same size in all dimensions. If so, then great. the operation can be carried out directly as the elements line up, just like in our previous slide. However, if not, it will check whether one of the arrays has a size of 1 for that dimension. If that's the case, then it replicates the array along this dimension of size 1 until it's the same size as the other array. So this is a little confusing, so I'm going to show you how it'll work concretely, and you'll see it's pretty straightforward actually. So to start, we take that original matrix, that 2D array that we were working with before. So to get the first array for our broadcast subtraction operation, we again reshape this 2D array into a 3D array. So we have one copy of that matrix again sitting in the first dimension. We then repeat this, but this time we reshape that same 2D array so that we have one copy sitting in the second dimension. This is also a 3D array, but this time that one copy sitting in the second dimension. So what happens when we try to subtract one of these arrays from the other in NumPy? Well, NumPy matches up each dimension and it checks the size of each. So as we've got a matching size in that last dimension, and we've got a 1 here and a 1 here, it knows that it can broadcast. So the way that it does this is it stretches that first array so that there are 3 copies along the first dimension, and it stretches that second array so there are 3 copies along the second dimension. And now everything lines up and it does the subtraction, and as a product of that subtraction, we end up with a 3 by 3 by 4 array containing the differences. Pretty nice, right? So let's have a look at how we can implement this in NumPy. So we'll jump back over to PyCharm. Okay, so you can see we've made even more drastic changes than last time. So we've gotten rid of the 2 separate functions to calculate and apply the Manhattan distance, and we're able to do it all in one pass now. So what we do is we pass in all of the train observations and all of the test observations as 2D NumPy arrays. And here is where the magic happens. This is the broadcasted subtraction operation. What we do is we recast that 2D array into a 3D object using this slicing notation. Where the none is, it sets a size of 1 for that dimension, and where the colons are, it basically leaves that dimension as the same size. And so basically, because we have a 1 in this first dimension and in the second dimension, and this matches up and this matches up in the terms of the same size, just like in the previous example I showed you, you can do that broadcasted subtraction operation. And what we end up with is a 3D array containing all the differences, just like I explained in the previous example. Then, because it's just a 3D array, we can apply the NumPy absolute differences operation to it, just like we did with our 2D array. And then what we do is we sum along that last dimension, and we get a 2D array containing all of the pairwise differences just in one pass. It's very elegant. So let's see how much time this has managed to save us. So, for the small data set, we're now down to 1.5 seconds. For the medium, we're down to 1 second. And for the large, we are down to 3 minutes. Pretty nice, right? So going back and comparing this to baseline, we're now between around 10 to 13 times faster than we were with the original loop implementation. But there are some additional improvements we can make. Oops. So most of the improvements that we've done, or all the improvements, have been to calculating the distance calculation, that Manhattan distance. But we haven't touched the code to implement k-nearest neighbors itself. That's all entirely in lists. So let's see how we can get some speed here. So if we have a look at our function for finding a test point's nearest neighbors, we can see a couple of problematic bits of code. The first is a sorting operation. These are always expensive. And then we have a list comprehension here in order to extract each of the labels. So why are these problematic? Well, firstly, let's start with sorting. Sorting lists in Python is locked to a single sorting algorithm, which is called timsort. And in contrast, the NumPy methods for sorting, sort and argsort, have a bit more flexibility. So for example, when no method is specified for sorting, NumPy sorting will default to quicksort, which is a bit faster. And then even when stable sorting is selected for NumPy, the sorting type will be adjusted to suit the data type of the array. So remember, lists can have mixed data types, but arrays are locked to one data type. And then apart from sorting, we have a final issue with this function, which is that list comprehension. So list comprehensions can function kind of like loops. And so this is likely causing another bottleneck, having to loop just to get those labels out. So let's see how we can make this a little bit more efficient. Oops, sorry. So let's jump into our last code example. So if we go down to our function to calculate the nearest neighbors, we're still doing this for one training point at a time, but instead of passing in those distances and those labels as lists, we're now passing them both in as one-dimensional NumPy arrays. If we go down to here, what we then do is use the NumPy VStack method in order to put them together as a single two-dimensional array, a matrix essentially. And then this is where the magic happens on this line. What we then do is we sort that 2D array by the vector, which contains all of those distance measurements. And we basically get the closest distant measurements to the most distant ones. Then what we do is we select the top K, and we use this slicing notation in order to detach just that vector or just that array that contains the labels. So this time we're not sort of having to loop through everything. We can just slice it off, and that saves us quite a bit of time. So that's it. Let's scroll down and see how fast our code is now. We're now down to 13 milliseconds for the smallest sample, 15 seconds for the medium sample, and 2.5 minutes for the large sample. And remember, we started with almost 40 minutes for the large sample. So if we have a look at this as a function of our baseline, we're down to 15 times faster for the large data set, 50 times faster for the medium, and over 1,000 times faster for the smallest data set. And these seem very impressive, but from looking around and seeing what other people are able to do with vectorized operations, this is pretty typical from what I've seen when people are using these operations. So you should be able to get similar gains for your own code. So to end, as I promised, I just want to explain at a high level why it's actually faster to use arrays rather than lists and loops, because to be honest, I didn't really understand this and I got very curious and decided to dig in. So let's have a look at how Python stores variables in memory. Let's say that I create a variable A, and that's going to have a place where it lives in memory. And let's say I then create a separate variable C. It's going to have its own place where it lives in memory. So as you can see in this illustration, obviously it's very simplified, but these memory addresses, even though I've created these variables in the same program, may not be sequential or even close to one another. The thing is that memory is massive. So in order to use it more efficiently, it's divided into blocks called pages. So the way that I think of pages, because I'm not a system administrator, is I think of pages like postcodes in the UK. And if you're not familiar with them, they tend to refer to a really small number of addresses. So for example, my sister lives in the UK. She lives in this residential neighborhood in a small city, and her postcode includes her house and around 5 of her neighbors. So the page division, as I said, it makes it easier for memory to work with in the same way that the postcodes make it easier for the Royal Mail to deliver letters. So the CPU is really lazy, and it's not going to do operations unless the variables are physically close to it. So it means that if I want to do an operation with A, you can see it's been moved so that it's physically right next to the CPU. This is akin to if the post office needed to move my sister's house and all of her neighbors right next to the post office to deliver a package to her. Fortunately, even though the Royal Mail is quite inefficient, it's not quite that bad. So how does this work with lists? So let's say we create a Python list here, and it has 5 elements. So unlike what I had expected when I first started reading about this, each element of the list is not actually stored in the same area of memory. So you can see that here in this illustration, that basically each element may not even be stored on the same page. So let's say that happened with this list. Every element is on a separate page. What happens when we try to do an operation on this list? This happens. As you can see, for every single element, the entire page needed to be moved to the location next to the CPU. And each page is around 4 kilobytes, which means that for each element in the list, 4 kilobytes of memory is being moved. And you can imagine this is the main thing that makes looping over a list so slow. But there are a couple of additional things. As lists allow mixed data types, the interpreter must actually check the data type of each element before running the operation. And this includes checks like seeing whether the operation you want to perform is even valid. You can have a list that contains a combination of strings and ints. You can't take a substring of an int, so that's going to be an invalid operation. So in contrast, let's say I create this NumPy array here. This array contains the exact same information as the list, but the difference is now each of these elements are stored in a contiguous block of memory. There's now a good chance that the elements of a matrix that I want to work with that's stored as a NumPy array are going to be spread over just a few pages. And this cuts down, obviously, on the number of pages that need to be moved to run my operation over the whole array. In addition, of course, as arrays are locked to a single data type, we already talked about this, this makes it easier to subset the array using indexing. And it also means that the interpreter knows the data type of each element in advance, so it doesn't need to do that check. And then finally, certain NumPy operations can be parallelized using a type of processing called SIMD, or single instruction multiple data. So this means that the data within an array can be broken into blocks and the operation can be run over each in parallel. And this adds another speed boost compared to the entirely sequential processing that I talked about that loops lock us into. So that is it. I hope that gave you a grounding on why NumPy's vectorized operations work the way they do and when and where it can be helpful to apply them. So here are my details. I'm on Twitter. I'm pretty active there. I'm on Mastodon, not so active there, but please do reach out if you're on there. And then finally, I run a blog. I actually do have a series that covers some of the same stuff that I talked about in this blog post and a lot more, in this talk, and there's in a lot more detail. So please do visit if you're interested. And then finally, if you want to play with the notebooks yourself, feel free to scan this QR code. It'll take you directly to the GitHub repo and you can have a look at the code yourself. Thank you so much.